Picture a star 40 times the mass of our Sun, burning at its core for millions of years, then, in a single second, collapsing inward so violently that nothing survives. Stellar black holes form when massive stars exhaust their nuclear fuel and implode. The outer layers explode outward as a supernova. The core crushes down past any known stopping point. What remains is a region of space-time where gravity is so extreme that escape velocity exceeds the speed of light. Most stellar black holes sit between 5 and 20 solar masses. They are the most common type in the universe. Astronomers estimate the Milky Way alone contains hundreds of millions of them. The first confirmed one, Cygnus X1, was identified in 1971 through X-ray emissions. It stripped from a companion star. That stripping is the tell. You cannot see the black hole directly, but you can see what it does to everything around it. Supermassive black holes. Deep at the center of nearly every large galaxy, something monstrous is sitting quietly. Supermassive black holes range from 1 million to tens of billions of solar masses. The one at the center of our own galaxy, Sagittarius A star, clocks in at about 4 million solar masses. Astronomers confirmed its existence by watching stars orbit an invisible point for decades, stars moving at thousands of kilometers per second around nothing visible. The record holder so far is TON 618, a black hole weighing 66 billion solar masses. How these giants formed is still one of the biggest open questions in astrophysics. They could not have grown purely by swallowing stars one at a time. The math does not work across cosmic timescales. Something faster must have happened. Direct collapse, mergers, early universe seed black holes. The models compete and none fully wins. What we know is that when supermassive black holes feed actively, they become quasars, outshining entire galaxies, intermediate black holes. For decades, astrophysicists had a problem. Stellar black holes topped out around 100 solar masses. Supermassive ones started at 1 million. The gap in between was embarrassingly empty. Intermediate black holes, ranging from 100 to 100,000 solar masses, were theorized but stubbornly refused to be confirmed. Then in 2020, gravitational wave detectors caught the merger of two black holes producing a remnant of about 150 solar masses, squarely in the intermediate range. The detection, called GW190521, was the first hard evidence the middle tier actually exists. Why does the gap matter? Because intermediate black holes may be the seeds that eventually grew into supermassive ones. Finding them means finding a chapter of cosmic history that was previously invisible. The hunt is now focused on dense star clusters, where repeated mergers could build mass quickly. The machine that creates the giants may finally be coming into view: primordial black holes. Go back to the first second after the Big Bang. The universe is not yet a second old, and it is not smooth. Density fluctuations ripple through the infant cosmos. In regions where matter packs too tightly, gravity wins immediately, collapsing patches of the early universe directly into black holes before any star ever forms. These are primordial black holes, and they may have masses anywhere from a fraction of a gram to thousands of solar masses. The wildest claim attached to them is this: they might be dark matter. A significant fraction of the universe's invisible mass could be black holes formed in the first moments of existence, drifting invisibly through galaxies ever since. Stephen Hawking spent years calculating their properties. Searches using gravitational microlensing have constrained but not eliminated the possibility. No primordial black hole has been directly confirmed. But the absence of a detection is not the same as an absence of existence. The search is very much alive. Rotating black holes. Most black holes in the real universe are not sitting still. They spin. A rotating black hole, described by the Kerr solution discovered by mathematician Roy Kerr in 1963, is a fundamentally different beast from its non-rotating counterpart. The spin drags spacetime itself around the black hole in a phenomenon called frame dragging. There is a region outside the event horizon called the ergosphere where spacetime is forced to rotate with the black hole. Nothing inside it can remain stationary relative to distant space. The Penrose process, proposed in 1969, suggests that energy can actually be extracted from a spinning black hole by exploiting the ergosphere. Some astrophysical jets, Beams of matter fired at near-light speed from active galaxies may be powered exactly this way. The faster the spin, the more extreme the distortion. Some black holes are estimated to be spinning at more than 90% of the maximum physically possible rate. The geometry around them is so warped that the rules of space and time barely resemble anything we experience on Earth. Charged black holes. In theory, a black hole can carry electric charge. The Reissner-Nordström solution, worked out in the early 20th century, describes a non-rotating but electrically charged black hole. Add rotation and charge together and you get the Kerr-Newman black hole, the most general solution general relativity allows. Here is the catch. Astrophysicists believe real black holes in nature are almost certainly electrically neutral. Any charge would be neutralized almost instantly by attracting opposite charges from surrounding plasma. Charged black holes are primarily theoretical tools, but they are extraordinarily useful ones. The mathematics of charged black holes predicts something extraordinary: multiple event horizons. An outer horizon and an inner horizon, called the Cauchy horizon, stack inside each other. The inner horizon is where determinism itself may break down, where the equations suggest the future becomes unpredictable, even in principle. Whether the Cauchy horizon actually survives in a real black hole or gets destroyed by quantum effects is a question physicists are still actively arguing. Micro-black holes. This is where the physics gets genuinely strange. Quantum mechanics predicts that at the Planck scale, distances of about 10 to the power of negative 35 meters, space-time itself becomes foamy and unstable. In principle, micro-black holes could form and evaporate almost instantaneously at that scale. Some theories with extra dimensions predicted that the Large Hadron Collider at CERN might produce micro-black holes in particle collisions. The idea triggered public panic before the LHC switched on in 2008. Newspapers ran headlines about the end of the world. Physicists patiently explained that even if micro-black holes formed, they would evaporate via Hawking radiation before traveling even a single atomic's diameter. The LHC ran. No micro-black holes were detected, but their theoretical existence opened a door. If extra dimensions exist and gravity leaks into them, the energy threshold for black hole formation drops dramatically. The collider experiments constrained the models but did not kill them. Hawking radiation black holes. In 1974, Stephen Hawking made a calculation that shook physics to its foundations. Black holes are not perfectly black. They glow. Near the event horizon, quantum effects cause pairs of virtual particles to pop into existence constantly. Occasionally, one falls in and one escapes. The escaping particle carries energy away from the black hole. Over time, the black hole loses mass and eventually evaporates entirely. For a stellar mass black hole, the evaporation time exceeds the current age of the universe by an incomprehensible margin. But for tiny black holes, evaporation is rapid and explosive. The final moments of a black hole's evaporation would release a burst of energy equivalent to millions of nuclear weapons. The deeper problem Hawking radiation created is the information paradox. If a black hole evaporates completely, what happens to the information about everything it ever swallowed? General relativity says it is gone. Quantum mechanics says information cannot be destroyed. Both cannot be right. Physicists have been fighting about this for 50 years and have not fully resolved it. Naked singularities. Every black hole has an event horizon, a surface of no return that hides the singularity inside. Roger Penrose proposed in 1969 that this is not accidental. He called it cosmic censorship. Nature always wraps singularities in horizons, hiding the breakdown of physics from the rest of the universe. A naked singularity would be a singularity with no horizon, a point of infinite density exposed directly to the cosmos. General relativity's equations do allow solutions with naked singularities. The question is whether they can actually form from realistic starting conditions. Numerical simulations have found edge cases where collapsing matter might produce one. If a naked singularity exists, it would be a point where the laws of physics as we know them simply stop working, visible to any observer with a telescope. Penrose's cosmic censorship conjecture remains unproven. It is one of the most important unsolved problems in classical general relativity. Black hole mergers. On September 14, 2015, at 5:51 in the morning Eastern Time, two detectors in the LIGO experiment registered a signal lasting less than a second. The signal was the gravitational wave produced by two black holes, each roughly 30 solar masses, spiraling together and merging 1.3 billion light-years away. The event, GW150914, was the first direct detection of gravitational waves and the first direct observation of a black hole merger. In the final fraction of a second before merger, the two black holes were radiating more power in gravitational waves than all the stars in the observable universe combined emit in light. The merger produced a single black hole and converted roughly 3 solar masses of material directly into gravitational wave energy. Since 2015, LIGO and its partner detectors have catalogued dozens of mergers. Each one is a map of spacetime itself vibrating. The data has already overturned assumptions about how massive black holes can grow and how common they are: quasar-powered black holes. In the 1960s, astronomers catalogued objects that looked like faint stars but emitted radio waves with bizarre intensity. They called them quasi-stellar objects, quasars. The mystery deepened when their redshifts revealed they were not nearby at all. They were billions of light-years away, meaning they were almost incomprehensibly luminous. The answer, confirmed over decades, is that quasars are supermassive black holes actively feeding. As gas and dust fall inward, they form an accretion disk that heats to millions of degrees and outshines entire galaxies. The most luminous quasar known, J0529-4351, emits energy equivalent to 500 trillion suns. A single black hole. The feeding does not last forever. As the black hole clears its surrounding material, the quasar dims. Our own galactic center was likely a quasar billions of years ago. What remains today is Sagittarius A star, quiet and relatively starved. The violence that shaped the Milky Way is written in the structure of the galaxy itself: black hole shadows. On April 10, 2019, the Event Horizon Telescope collaboration released an image that stopped the world. It was a blurry orange ring with a dark center, the shadow of the supermassive black hole at the center of galaxy M87 55 million light-years away. The shadow is not the event horizon itself. It is the region where light paths curve so severely that photons either fall in or orbit in unstable rings. The dark center is the photon capture zone. The image confirmed predictions made by general relativity with striking precision. In 2022, the same collaboration released an image of Sagittarius A star, the black hole in our own galaxy. Capturing it was harder. Sagittarius A star is smaller, and its surrounding gas moves faster, blurring the image rapidly. Both images represent the boundary between what we can observe and what is permanently hidden. The shadow is the last thing light can show us before the universe seals itself off.